ठीक है, स्टार्ट करते हैं। So in last class we have solved some problem related to the Bernoulli equation. Today we will solve some more problems. So basically these are the derivations for the special cases. ठीक है, स्टार्ट करते हैं। So in last class we completed one problem related to the Bernoulli equation. Today we derive formulas for some special cases related to the, which is also from the Bernoulli equations, which are related to the Bernoulli equations. So first is rate of flow, determination of rate of flow from the pressure measurement. Okay. So I am writing the problem statement. A liquid with a constant density rho kg per meter cube is flowing in at an unknown velocity v1, is flowing at an unknown velocity v1 meter per second through a horizontal pipe of cross-sectional area a1, through a horizontal pipe of cross sectional area capital A1 meter square at a pressure P1 Newton per meter square. Okay, this is the pressure at this point. Okay, then passes through a section where area of the tube is gradually reduces to A2 meter square. Area is reduced gradually to A2 meter square. Okay, and the pressure is P2. P2 Newton per meter square. Okay. Okay. Now, assuming no friction losses, calculate the velocity v1 and v2. Assuming no friction losses, calculate the velocity v1 and v2. Okay, so basically it is given that there is a pipe. Okay, I will make the diagram in the next page so you can understand. So it is given that a fluid with a constant density rho is flowing at a known velocity v1. So velocity is not known. v1 value you have to determine the value of v1 and v2. Okay, through a horizontal pipe of the cross section area a1. A1 value is given. The cross section area of the pipe is given at a pressure P1. The pressure value is given. Then passes through a section where area is reduces gradually to the A2. Now the cross-sectional area is pipe is changed from the A1 to A2, which is lesser than the A1. Okay, and the pressure is changed from P1 to P2. Okay, now calculate the velocity, the values of the velocity V1 and V2. Okay, so first we will make the diagram. So this is a pipe, then the cross-sectional area is reduced gradually. Now you have the less cross-sectional area pipe. This is the basic diagram. Here you have the, this is point 1. Here you have the velocity v1 and the pressure at this point is P1. Here you have the velocity v2 and pressure at this point is P2. So this is the horizontal pipeline. Now the cross-sectional area of this tube is A1. The cross-sectional area of this tube is A2. So if you assume there is a no friction loss, then calculate the velocity v1 and v2. This is your problem. Okay. So first we will start with the equation of continuity. So here we will use the equation of continuity at a macro level, not the micro level. Okay. So what the equation of continuity says that the mass is conserved. Okay. So mass is conserved means mass flow rate at point 1 and 2 should be equal. And the mass is conserved means whatever the liquid is entering from this point, the same liquid will leave from this point. The mass will not change. Okay. So the point 1 and points 1 and 2 should be equal. Okay. Now you can write, suppose mass flow rate is m1 at the point 1 and m2 is the point 2. So you can write m1 equal to m2. And what is the value of m1? M1 can be written as density multiplied by volumetric flow rate Q1. Density rho is constant. Here you can write density as a rho multiplied by volumetric flow rate is Q2, where rho is density and Q1 and Q2 are the volumetric flow rates. At points 1 and 2 respectively. Okay. Now this rho will be cancelled out because rho is constant. It is given in the equation. The liquid has the constant density rho1, rho. So rho is constant. You can cancel out the rho. Now you will get the Q1 equal to Q2. Now you can write Q1 equal to Q2 as A1 V1 equal to Q1 yani Q1 equal to volumetric flow rate, that is the cross-sectional area multiplied by velocity. A1 V1 equal to A2 V2. So this is the equation of quantity for the incompressible fluid if you have the single pipeline. Okay, so A1 V1 equal to A2 V2. Okay, now from this equation you can write V2 equal to A1 V1 divided by A2 okay, A1 V1 divided by A2. Now you can use the Bernoulli equation. Okay, so the Bernoulli equation in this case will be Z1G plus V1 square by 2 alpha plus T1 by rho should be equal to Z2G plus V2 square by 2 alpha plus T2 by rho. Okay. So first we have done the material balance. Now we are doing the mechanical. Bernoulli equation is nothing but the mechanical energy balance. Okay, now we are doing the mechanical energy balance. So this equation is true for the steady state conditions and the non-compressible fluid. Bernoulli equation will not true for the compressible fluid, because in the compressible fluid you can easily change the mechanical energy to the thermal energy. If you compress the fluid, the temperature will increase. If you expand the fluid, the pressure will reduce. With pressure, the temperature will reduce. Because the temperature itself represents the movement of the kinetic energy of the molecules. So when you compress the kinetic energy of the molecules at the micro scale, Okay, that is the definition of the temperature in the quantum mechanics. Okay, so when you compress the fluid, a gas, so what will happen? The mechanical and the kinetic energy, due to the higher collision between the molecules, the kinetic energy of the molecules will increase. So you will convert the mechanical energy to the thermal energy. Okay, but so mechanical energy cannot be conserved. Okay, but in this case, the Bernoulli equation is only true. Here, this is the conversation of the mechanical energy only. The kinetic energy plus potential energy plus pressure energy. So these are the mechanical energy. So there is no thermal energy here. Okay, so you have to take care of the mechanical energy only. You have to solve this equation for the incompressible fluid only. Okay, now this tube is the horizontal tube. So Z1 equal to Z2. You can write Z1 equal to Z2. So these two points will be cancelled out. Also, you can assume the turbulent flow, because these equations are generally used for turbulent flow only. So alpha equal to 1. Okay, so this equation will reduce to V1 square by 2 plus P1 by rho. That should be equal to V2 square by 2 plus P2 by rho. Okay, now you can substitute the value of V2 in terms of V1, which we had calculated here. So this is equation number 1, this is equation number 2. Substitute the value of V2 from the equation number 1 to the equation number 2. You will get P1 square by 2 plus P1 by rho. That should be equal to, so instead of V1 square, you have V2 square, you have the A1 by A2 V1. Okay, so here it will become V1 square multiplied by A1 square divided by A2 square divided by 2 plus P2 by rho. Okay, now you can just rearrange this equation. This will become, just rearrange this equation, this will become P1 by P2, P1 minus P2 divided by rho should be equal to, this V1 goes here and you can take V1 common. So it will become V1 square in bracket A1 divided by A2 whole square minus 1. Here V1 by 2. Okay, now just rearrange this equation because you have to calculate the value of V1. So V1 becomes under root of P1 minus P2 divided by rho multiply by 2 divided by A1 by A2 whole square minus 1. Okay, so this is the value of V1. Now you can use this is equation number 3. Now substitute the value of equation of V1 from equation number 3 to equation number 1. You will get the value of V2. Okay, so when you substitute equation number 3, V1 from equation number 3 to equation number 1. Okay, so what you will get? V2 equal to A1 by A2 multiply by under root of P1 minus P2 by rho multiply by 2 by A1 by A2 whole square minus 1. Now, if you take this A1 by A2 inside the root, it will become A1 by A2 whole square, and just rearrange the equation, you will get this expression. P1 minus P2 divided by rho multiply by 2 divided by 1 minus A1 by A2 whole square. So this is the value of V2, and this is equation number 4. And from equation number 3, you have the V1, that is equal to under root of P1 minus P2 by rho.
एक्सक्यूज मी सर,
हाँ बोलो
सर फोर्थ वाली क्वेश्चन में A2 बाई A1 नहीं आएगा नीचे?
हाँ, A2 by A1 हो जाएगा. Okay. Now this is the V1. A1 by A2 whole square minus 1. Okay, this is equation number 3. So these are the value of velocities. Okay, so once you know the pressure drop, which you can calculate from the manometer, already in the experimental class you have studied how to calculate the pressure drop, which is very easy to calculate, है ना? And if you have the two different diameter of the pipelines, you can calculate the, if you know the pressure drop, you can calculate the values of the velocities. Only by the pressure drop and the dimension of the pipeline. You even don't require any other measurement. You know, just take the value of the that is the basic principle of the venturimeter. है ना? Venturimeter में ही करते हो आप. Basically, you just calculate the pressure drop in between the two different size of the pipes, and then based on that pressure drop, you can calculate the value of the velocities. Now the next problem, rate of flow from a nozzle in a tank. So I am writing the problem statement. A nozzle of cross-sectional area A2 is discharging to the atmosphere and is located in the side of a large tank. Okay, in which the open surface of the liquid is the large tank. The open surface of liquid in the tank is h meter above the center line of nozzle. Okay, so the open surface of the liquid in the tank is h meter above the center line of the nozzle. Okay, calculate the velocity v2 in the nozzle and volumetric flow rate of the discharge if no friction losses are assumed. Now what you have to calculate? Calculate the velocity v2 and volumetric flow rate of discharge if no friction losses are assumed. If no friction losses are assumed. Okay, so the problem is you have a large tank, and in this tank you have a nozzle. This is a nozzle. So fluid is flowing from the nozzle. There is a one. This is the point number 2. So velocity at this point is v2. So you have to calculate the velocity v2 from this point to the top surface of the liquid is h. So this distance is capital H. Okay. Suppose this point is 3 and this point is 1. Inside the nozzle, the point in the liquid is 1. Okay. Now what you have to do? You have to do the mechanical energy balance. So you have to use the Bernoulli equation in between pipe 1, point 1 and point 2, and then point 3 and point 1. Okay. That will give you the actual value of the, that will give you the actual value of the velocity. Once you know the velocity, you will get the value of the final you will get the value of the final volumetric flow rate. Okay, so you have to solve the problem first. Do the Bernoulli, use the Bernoulli equation between point 1 and point 2, then solve the Bernoulli equation between point 3 and point 1. Okay, so I will try to solve in this place only, this space only. Okay, so you can understand. This is the diagram. First, we will solve the equation between point 1 and 2. Okay, so in between point 1 and 2. So V1 equal to, because it is inside the tank, so the cross-sectional area at this point is very large. Okay, so you can assume, because cross-sectional area is very large, so the movement of the molecule is very small, and that is negligible. So you can assume that velocity is 0 at the point 1. Okay, so V1 equal to 0 at this point. The second point is because these 2 points are at the horizontal position, so the elevation is 0 between the point 1 and point 2. So Z1 equal to Z2. You can assume that the elevation is equal to Z1 equal to Z2. Suppose the pressure at inside the tank is P1, and outside what is the pressure? That is the 1 atmosphere. Or you can write 1 atm, or you can write this pressure is P2, which is equal to the 1 atm. Okay, so you can write the equation now. Z1 G1 plus V1 square divided by 2 plus P1 by rho, that should be equal to Z2 G2 plus V2 square by 2 plus P2 by rho. Okay, so these two quantities will be cancelled out, because Z1 equal to Z2, V1 equal to 0, this will be 0. So you will get V2 equal to, from this equation you can calculate the value of V2. So V2 equal to under root of 2 P1 minus P2 divided by rho, meter per second. This is the linear velocity, average linear velocity. Now here V2 is defined as the function of P1 and P2. Okay, now P1 and P2 equal to, because P2 equal to P3, suppose here pressure is P3. Okay, so you can say P1 minus P2 equal to P3 minus P1. Okay, because P1 equal to P3. Okay, so P1 equal to P3 equal to 1 atmosphere. Okay, so both are the 1 atmospheric pressure. So you can say P1 minus P2 equal to P1 minus P3. Okay, so these two points. Now you have to solve the Bernoulli equation between point 3 and point 1. So point 3 and point 1. So velocities at both points are 0. So V2, V1, why the velocities are 0? Because the surface, the cross-sectional area of tank is very large. So whatever the movement of the molecules are there, that are very small, negligible. So you can assume that the velocities are 0, V1 and V3 are 0. Now the difference between the elevation is Z3 minus Z1, Z3 minus Z1, that should be H. Okay, so you can write Bernoulli equation. So Z1 G This is not G1 G2, this is G only है ना, gravity only. Z1 Z plus P1 square by 2 plus P1 by rho equal to Z2 Z Z3 G plus V3 square by 2 plus P3 by rho. So V3 and V1 will be cancelled out because both are 0. Now just rearrange this equation. You will get Z3 minus Z1, that is equal to Z3 minus Z1 G, that is equal to P3 P1 minus P3 divided by rho. ठीक है, just rearrange this equation. Now P1 minus P3 equal to P1 minus P2. So this will be equal to P1 minus P2. Once you substitute the P1 minus P2, just suppose this is equation number 1, this is equation number 2. To substitute the value of equation number 2 in equation number 1, you will get V2 equal to under root of 2 G Z3 minus Z1 equal to H. So Z3 minus Z1 equal to H. So V2 is, now we will use the next page, V2 equal to under root 2G H. Okay. Now if the cross-sectional area of the pipe is A2, then just multiply by A2, you will get the volumetric flow rate. So Q2 equal to A2 multiplied by inside under root of 2GH. So this is the flow rate of the from the nozzle in a tank. So in respect to what is the size of the nozzle, the velocity will be constant. Velocity will only depend upon the height of the water inside the tank. And now, if the tank diameter is large, tank diameter is small, it will not change. The velocity will not change. And the velocity will only depend upon the height of the water column in the tank. It will not depend upon the diameter. Okay, that you can also observe in the experiments. And the velocity from the tank will depend only upon the height of the water column. Okay, so this is the formula to calculate the flow from a nozzle inside a tank. Now we will solve one more problem. So friction loss in a sudden enlargement. So basically I have already given you the formula. You have to just uh, derive the formula here. So there is a pipe of the, suppose this is the point 0, this is the point 1, and this is the point 2. So fluid is flowing, fluid, a constant density fluid is entering in the pipe. So at the point 0, velocity is V0. Now the diameter of pipe suddenly changed, suddenly increased. So you have the higher diameter of pipe. So what will happen when the diameter is increased? The velocity will reduce. At the same time, you have the the velocity will reduce. At the same time, you have the high pressure. Kinetic energy will reduce, potential energy will remain same, but the pressure energy will increase. Okay, so you have to calculate how much friction loss is there inside the pipeline. Okay. So we will divide the section in the 3 points. This is the point 0, this is point 1 and point 2. Okay. Now we will also use the macro scale momentum balance here. We will use the macro scale momentum balance as well as the macro scale momentum balance as well as the mechanical energy balance to solve this problem. Material balance also to solve this problem. Okay. So what will happen? Once the fluid approaches to the point 1, the velocity will not change suddenly. The change in velocity will take time. So till point 2, the velocity will change gradually. At the point 1, you suppose you have the velocity v1 here. So v1 and v0 should be equal. Okay. So velocity will not change suddenly in between these 2 points, although the diameter has changed. So here v0 equal to v1, and because velocities are equal, then the pressure energy will also not change. So you have the p0 equal to p1. Okay. Now what we will do? We will do the mechanical energy balance in between these 2 points. Okay. And point 1 and point 2 area is equal. Here the area is A1 and here the area is A2. So you have the A1 equal to A2. Area between these 2 points are equal. Okay. Now just first we will do the material balance, macro scale material balance. Okay. So V0, suppose the density of fluid is rho, V0 rho multiplied by A0, that should be equal to V2 rho multiplied by A2. So in between the point naught and 2, if you do the material balance, so this is the material balance, m naught equal to m2. So just rearrange this equation, rho will be cancelled out. So V2 equal to, you can write V2 equal to A0 divided by A2 multiplied by V0. So this is the V2 in terms of V0. Okay, from the material balance. Now you can do the momentum balance. So here momentum, there are 2 terms. Momentum is basically the force balance. So you have the velocities as well as you have the diameter. Okay, so A1 equal to A2. So you can use either A2 in both points, but here pressure is P0, here pressure is P1. So P0 equal to P1. Okay, so you can write P1 A2, this is the pressure of force at this point, should be P1 A2 minus P2 A2, the pressure force in this point. So the difference between the pressure force, that should be equal to mv2 minus mv1. M is the mass flow rate, and the mass multiplied by velocity, that will become the momentum. Okay, so mv2 minus mv1. Okay, now just substitute the value of p2 from this equation. Okay, and rearrange the equation, you will get A2, you can take common A2 in this case. So just I am substituting P1 minus P2. A2 you can take common. That should be equal to M multiplied by A0 by A2 V0, and V0 equal to V1. So you can instead of V0 you can use the V1, M multiplied by V0, because V1 equal to V0. Okay, now also you can substitute the value of M. Okay, so M equal to mass flow rate, M is the mass flow rate, so M equal to V0 multiplied by rho multiplied by A0. So A2 P1 minus P2, that should be equal to, I am taking the A common, that is equal to rho multiplied by V0, and this V0 will also come common, so V0 square multiplied by A0. Okay, so A0, and in bracket you will get A0 by A2 minus 1. Okay, so this will be equation. Now you can take this term, you just rearrange this equation, you will get, slightly rearrange this equation, you will get V0 square A0 by A2 in bracket 1 minus A0 by A2 bracket close should be equal to P2 minus P1 divided by rho. This is equation number 1, this is equation number 2. So this equation expression comes after material balance and momentum balance. Okay, now we will do the mechanical energy balance. Okay, so we will do the mechanical energy balance between the point 1 and 2. Okay, so what is the point 1 and point 2? This is the point 1 and this is the point 2. So velocity will change. Here velocity is v1, here velocity is v2. So the velocity is changing, the elevation is not changing, so the potential and the difference in the potential energy will be zero. Pressure is changing. Here you have the pressure P1, here you have the pressure P2. So P1 to P2 pressure is changing. Here you have the pressure P0. Okay, so we will do the mechanical energy balance based on these three quantities. Okay, so again you have the friction losses also. So V0 square minus V2 square, और V1 स्क्वायर माइनस V2 स्क्वायर, V1 इक्वल टू V2 हो जाएगा. First we will write the mechanical balance. 1 and 2. Okay, so you can write V1 square minus V2 square divided by 2 minus sigma f. This is the friction losses. Here we have to calculate the friction loss equal to only, that is equal to P2 minus P1 divided by rho. Okay, now we know that V1 equal to V0. From initial assumption we can say, so you can write in place of V1 just write V0 square minus V2. In place of V2 you can use A0 by A2 multiply by V0 square multiply by A0 by A2 square divide by 2 now minus sigma f, that should be equal to this quantity, है ना? So just open the bracket, you will get V0 square A0 by A2 minus V0 square A0 square divided by A2 square. Okay, now just rearrange this equation. So take this quantity here and rearrange this equation. You will get sigma f equal to, take sigma f in the right hand side, other quantity left hand side, other quantities in the right hand side. You will get sigma f equal to V0 will be common, V0 square by 2 will be common in all equations, in bracket so here it will come 1, this is the 1, so it will goes in this side, this it will remain here, so 1 minus here it will become 2 A0 by A2, then this quantity will remain, this will goes here, so it will becomes plus A0 square divided by A2 square. Just check it, है ना? This should be the answer. ठीक है? Now this will be the, this should be equal to sigma f, that should be equal to V0 by 2, V0 square by 2 in bracket, and it will become A square plus 2AB plus B square, A square minus 2AB plus B square. So it will become 1 minus A0 divided by A2 whole square. So this is the value of the friction loss in the sudden enlargement. ठीक है, समझ में आ गया डेरिवेशन? So here we have used the moment. First we done the material energy balance, then momentum balance, and at last the mechanical energy balance between these 3 points. Okay, velocities are equal, V0 and V1 are equal, P0 and P1 are equal, but the surface area at A1 and A2 are equal. Why the V0 and V1 are equal? Because the velocity will not suddenly change, and when the fluid, so it will take time to make the change the direction of the flow. Okay, so here the velocity will same, here you have the dead zone. Okay, so here you don't have any flow, in this zone. Okay, so the velocity, whatever the velocity is here, that the same velocity will be here. After some distance only you have the higher velocity, that's why you have the friction losses in this case. ठीक है, किसी को कुछ पूछना है इसमें? समझ में आया इस क्लास का? रिविजन समझ में आया?
यस सर।
ठीक है, तो फिर अच्छा, आप लोग का एग्जाम लेना है, एग्जाम कब रखें? 5 को रखें, मंडे को? 4 to 6, 5, 5th मंडे, 5th अप्रैल।
सर 5 अप्रैल को सीआरई का है।
तैयारी का एग्जाम है, तो कब दोगे
यस
फिर?
सर।
फिर आपकी 7 को क्लास है, 7th को, 7th को एग्जाम देखो दोगे? 7th वेडनेसडे।
7 ठीक है सर।
ठीक है, 7th को रखते हैं फिर। ठीक है, और इस वेडनेसडे को जहां तक हो जाएगा वो आएगा पूरा। ठीक है, तो इस वेडनेसडे को जहां तक सिलेबस हो जाएगा वो पूरा आएगा। ठीक है, 7th अप्रैल को रखते हैं एग्जाम। So we will solve 1 or 2 more problems only. So that will be your syllabus for the exam. चलो क्लास खत्म करते हैं, अब नेक्स्ट, अब मैं वेडनेसडे को मिलेंगे।